readily see what's big and what's small. So big values are indicated in red, and big in the image turns out corresponds to white, so it turns out that corresponds to that little area right there. Blue values are small, and that corresponds to black. So the grayscale values in between are somewhere in between. This is called a heat map because the big values are hot, they're red. The small values are cold, they're black. So this is just a very convenient way of looking at a plot of such a signal. However, here we have the same situation we just had with the digital signal. Looking at the image, the plot of the function, I have a hard time appreciating what it really is. It's a lot easier for me as a human to look at the image as opposed to a plot of it. But again, this is how the computer sees it. There's absolutely no difference between the two, and we're going to develop more insight into the presentation of information as we go through the course. Now, another kind of signal that's interesting is video. As you know, video is a sequence of images occurring in time, so that makes it a function of three variables. So, space and time. So, the jargon is that an image is a 2D signal because it depends on two variables. This is a 3D signal because it depends on three variables. And this is common terminology. So again, a one-dimensional signal was, for example, speech, what we saw earlier. But it can be a little bit more complicated than that, because if it's color video, it actually is three 3D signals rolled up into one, considered as a signal. So our color video actually consists of a red, a green, and a blue signal, each of which is a function of space and time. So this is a multi-valued signal. So this image up here is in color as an image, not as a plot, but as an image. And it's still considered a 2D image. So again, the dimension of a signal has to do with the number of variables upon which it depends, not how many values it may have. So this 2D image here has red, green, and blue components, each of which is a 2D signal. Now let's bring in information. Where's the information? So I'm going to say something controversial here, that information does not exist without a signal to represent it. So let's think about this for a second. I've already shown you that text is a signal. So all books contain signals from one viewpoint. Certainly there's more to it than just that. It's the structure of that signal that conveys information. You may say, well, information exists without there being a signal. For example, a memory that I have in my head. Well, it turns out that memory is mediated and brought to fore in your brain by electrical signals. And we'll talk about that a little bit. So there is no such thing as information just existing in and of itself without there being a signal to represent it. So signals and information are linked together in very important ways. Not all signals contain information, but information doesn't exist without there being a signal alone. So we talk about information being encoded in a signal by modifying its structure. That's why I was talking earlier about the structure of a signal, because that's where the information is. It varies the structure of the signal. That's how you think about it. So what we're going to do is look at this sine wave. So if I take this signal, which we've already talked about, has three parameters highlighted in blue here. If I change the amplitude of that signal in such a way that the amplitude varies according to the speech signal that I'm producing now, that turns out to be what's called amplitude modulation, and that underlies AM radio. If I change the frequency according to what I say, that gives you frequency modulation or FM radio. There is something called phase modulation, but it turns out it's not used very often because it's been shown that frequency modulation has better technical characteristics than phase modulation. But anyway, that's why I wanted to find out what the structural components of a sine wave were so that I can change those components according to the information I want to encode in. So what does a system do? Well, it's a system that operates on signals to produce a modified signal. So the system might do the encoding of information, and it also can do the extraction. It can also is the thing that extracts information. Now the way we indicate systems is with what's called a block diagram kind of thing. So here's the idea. The input to my system is X. It's always, in most drawings, comes in from the left side of this block box that denotes the system. The output is Y, usually comes out from the right. And so the arrow indicates the inputs and the arrow coming out indicates the output. So what this system does is it operates on the signal X, does something, who knows what, and produces an output Y. So we could go down the mathematical path to talk about functions that are functions of functions. So that path turns out to be overly complicated. We won't need to go down that path. We'll just learn and talk about systems as things that take as an input a signal and produce another signal. So here's that fundamental model of communication that I was saying earlier is so important. It's a sequence of systems. I've labeled important signals. The source, the idea is there's a source that has a message signal. And the goal of a communication system is to get that signal over to its destination, which technically is called the sink. I do not know where the term sink comes from. It's just the terminology it's used. We'll just go with the flow and use that terminology. But the idea of communication is to get something that contains information from one place to another. Now it turns out that'd be easy if it wasn't for this funky cloud-like thing in the middle, the channel. That's another system, but I've drawn it like this because this basically refers to phenomena we have no control over. And let me guarantee you that the channel, nothing good happens to a signal in a channel. What comes in is not what comes out at all. In fact, the channel can do things to signals that you may not know in great detail. So, trying to send the message M directly through this channel is a big mistake. In most cases, it won't get through. So here's what we do. We're going to take our message signal M and put it into a transmitter. And what the transmitter does is creates a signal which is better suited to go through the channel than the message M would be. This is called engineering design. This is what electrical engineers and communication engineers do. Try to get signals through the channel. So this is termed the modulated message. That's what a transmitted signal is. Transmitter is a box which takes the message M as an input and produces X as an output. That goes through the channel where nothing good happens and produces the received signal R, which is, trust me, is a corrupted modulated message. It's going to do all kinds of things. Nothing good happens in a channel. The receiver's job is to try to figure out what that message was that was being transmitted, despite the fact it's been corrupted. So I put this hat on top of the symbol here because it means that it's not exactly equal to m. So it's an approximation to m. So m hat basically equals the message m plus some error. And one of the things you want to do when you design communication systems is to try to fight the channel so that you can minimize that error. And it's this message m hat that goes into the sink, goes to the destination. That's what you get. It's known as the demodulated message. So here are all the labeled pieces of our fundamental model. We're going to talk about this again and again. We're going to worry about how transmitters are designed, how receivers are designed. Turns out you cannot design these without designing them together. And we will talk about that as we go through the course. So this is the fundamental model. You now know what a signal is, you know what a system is generically, and now we're ready to get serious and talk about things together.